Okay, so welcome back, everybody, if you've taken your short break. I'm Dr. Matt Pratola, and I'm an associate professor of statistics at Ohio State. So in the second half of today's event, we're going to dive deeper into the important scientific aspects of climate change with our guest, Dr. Hayhoe. If you are just joining us, Dr. Hayhoe is an atmospheric scientist whose research focuses on understanding what climate change means for people and the places we live in. She's an endowed professor at Texas Tech University, and she hosts the digital series Global Weirding on PBS, and has also been named one of Time's 100 most influential people and World Evangelical Alliance's climate ambassador. If you have been here for the morning talk that she gave, you will have already seen kind of how energizing her talks are and how she's able to convey the scope and complexity of this issue in a very receivable way. So this is really an amazing skill of hers. But in the science realm, her impact has been no less significant, with over 125 peer-reviewed publications and key contributions to the US government reports on climate, such as the second and third climate assessments. So her grasp of the science is certainly no less impactful. But personally, I find what is most, I guess, motivating about her is her scientific outreach work in working with cities and regions to bring the science, methodologies, and tools to bear on evaluating climate risk and risk mitigation strategies. And so this is really fascinating work where you can translate the science into effect. So I thought when I was talking to Katharine about this afternoon session, she thought it'd be kind of a fun story to maybe relate to you all how I first met her. So when I was a graduate student in statistics, I met her in the most atypical of ways. I was working on something called the R statistical computing languages used by many statisticians to run simulations and encode methodology onto the computer. But R has kind of well been known to be very slow. So it's good for prototyping, not good for production. And at the same time, one of the people I was working with during my graduate school needed some code to be sped up, and I came up with ways to speed up our code, and this got posted on the internet somewhere. And a few thousand miles away, Katharine and her team were working on statistical downscaling methods, which I think she'll talk a little bit about today. And they were using R, and their R code was running really slow, and it was not practically feasible. And so a short Google search by her later brought the two of us together. And later, during my postdoc years at Los Alamos in New Mexico, this was a very short ride away from Lubbock, Texas. So I went and visited, and I got to see her give a really fascinating talk on the effects of drought in Texas and these kind of real world impacts of climate change that they were seeing already over there. That would have been around 2011 or so. So really fascinating work that she's done, and it's been really a privilege to get to know her over the last decade or so. So with that, I'm very happy to reintroduce Katharine to talk to us about the scientific aspects and specifically about high resolution climate projections to quantify future impacts. As before, Nicole will post the Poll EV link in the chat window so that you can follow along with her talk in real time as she will demonstrate or instruct. So Katharine, please go ahead.
Great. Thank you, Matt. It's such a pleasure to be with you here virtually and to dig a little bit deeper into the science. So in addition to talking about climate change, I often do a lot of science too, and my science focus specifically on looking at how climate change affects us in the places where we live. So what we're going to be doing is, if you attended the previous talk, you know the drill. We're going to be taking questions via poll everywhere, which means that you can upvote questions as we go along, and I'll answer the most upvoted questions at the end. So I see that people are already putting some questions in the chat, but if you don't mind, please go ahead over to pollev.com/Katharine. I will put the link in the chat right here. Go ahead and type your question in there, and you can be putting your questions in anytime as I go along, but we'll get to the questions at the end. So again, if you have a question, put it in at pollev.com/Katharine, and then we'll see all those questions at the end, and you can go there at any time. So earlier, let me just share my screen here, just a second. There we go. Earlier, we were talking specifically about how we communicate on climate change. And I talked about how the type of information matters. Just to cast your memory back 2 hours, and if anybody wasn't here, that's totally okay. You can go back and watch it. It was recorded, but you don't need to for this presentation, because I just wanted to summarize some of the most important takeaways from the last talk to lead into this one. And one of the most important takeaways was the fact that when we look at the most politicized issues in the United States, the #1 issue is climate change. This is from February, but back 10 years ago, we saw the same result. And even as recently as August, climate change still tops the list for the most politicized issues in the US. And so we often think if we just fill up our wheelbarrow with facts and go dump them on people, science facts about melting ice sheets and rising sea levels and wildfires burning greater area, surely that will be enough to change their minds. But what we know from the social science is that the knowledge deficit model, which is the idea that we are blank slates just waiting to be written on by the correct information. The knowledge deficit model, while it is very successful for mathematics, 2 + 2 = 4, for black holes, people might not understand them, but they're willing to agree with the experts. It fails when we apply it to highly politically polarized topics. And Dan Kahan from Yale is a researcher in this area, and he found specifically that giving people more information on climate change, facts, and science is not the solution. And in fact, the smarter we are, the better we are to able to understand science, the more politically polarized we are by this information. And I showed this figure 2 hours ago, talking about how he asked people, is there solid evidence that global warming is due to human activities? And there was only a very weak correlation between something he calls ordinary science intelligence and the probability of answering correctly. But if you divide that out by political affiliation, all of a sudden, there is a very significant change. The truth is that climate science denial is not a cause, it's a symptom. It's a symptom of a much larger package of issues that today actually include coronavirus denial as well. And just like with coronavirus, we had early warnings. It was over 55 years ago now, or almost 55 years ago in a couple of weeks, that scientists first warned the US president about global warming. And there have been warnings of a pandemic in general, and specifically of this pandemic, well in advance of the lockdown, the quarantine, and all of the other actions that were taken. I mentioned last talk that we've known about climate change and the human role in it since the 1800s. But just as with coronavirus, when we thought it was distant, a type of pneumonia in China was how it was being referred to in January. In the same way, we think of climate change as a type of pneumonia far away in the future. I showed you how most people agree that climate change will harm plants and animals and future generations and people in developing countries, but we don't think it matters to us personally. But here's the interesting thing, and this is where we start to get into the type of information that matters, which is what my own research touches on. The interesting thing is that these numbers are starting to change. Now here on the left, you have a figure showing how many people were concerned about coronavirus. And you see that it started off around 40% in February, but by the time we got to the first week in March, after the first week in March, we were sitting at about 55 or 60% by the first week in March. Now cast your mind back to the first week in March. I know it feels like it was like 10 years ago, but what were you doing the first week in March? I was packing for Ireland. And it was one of my bundled trips where I'd spent 2 years lining up 18 different events to do in 11 days to minimize the carbon footprint. And coming from Canada, I had lived through the SARS and the bird flu and the swine flu. So I'm packing up my bag to go to Ireland in the 3rd of March specifically. And my husband says, "Do you think you should go?" And I said, having lived through the bird flu and the swine flu, I said, "Oh, yes, it's Ireland. I'll be fine." Well, famous last words. Fast forward, 6 days, I did manage to get, I think, like 9 of the 18 events done. And then within 24 hours, the whole country shut down. And within another 24 hours, it was illegal to travel more than 2 kilometers from your home. And luckily, I made it back just before that. So think back to that first week in March when we were just starting to realize that coronavirus was not distant. It was actually already here, and it had been for weeks. And it was affecting people who lived in the places where we lived. And guess what? When it comes to climate change, we are now at that same number. So our level of concern on climate change is where our level of concern was on coronavirus the first week in March. Isn't that interesting? Why has our level of concern been rising? In fact, it jumped the most it's ever jumped last year, and it's remained steady over this year. I think one of the biggest reasons is because we've seen the impacts here and now. We've started to see changes happening where we live. Both coronavirus and climate change, they are affecting us. They are affecting us today, and they're affecting us here. And that's why one of the most important things we need to be able to know so we can tell people is what's happening where we live. Now, at this point, you might say, sure, we can talk about what's already happening, but why do we need projections of the future? We need projections of the future because it's as if we're driving down a road. Now, here in Lubbock, or Lubbock, as my Canadian relatives prefer to call it, here in Lubbock, we have some very flat roads. It is very flat here on the high plains. And in fact, some of the roads are so dead straight that you could be driving down the road, looking in the rearview mirror, and you could stay in your lane. You literally could. Now, I'm not going to say I've tried this. I'm not going to recommend that you try it either, but that's how straight the roads are. Until at the top of this map, you get to a giant curve in the road. And this is a literal photograph of the curve with a row of concrete grain silos on the curve. What happens if you're looking in the rear view mirror and you get to the curve? Let's just say you'll end up somewhere you didn't plan to be. Planning for the future, which is what we humans do all the time. Our whole civilization is built on planning for the future. Our economy, our resource consumption, our retirement plans, all of our lives, our insurance, everything is built in planning for the future. But if we are planning for the future based on the past, it is like driving down the road looking in the rear view mirror. It works great when climate is stable. And although there have been some regional variations over the course of human civilization on this planet, climate has been as stable, the temperature of the planet has been as stable as the temperature of the human body, goes up and down by a few tenths of a degree over the course of a day. But now the planet is running a fever. Or to continue the road analogy, all of humanity is packed in a giant overcrowded bus, hurtling down the highway at 75 miles an hour. And we are about to hit a curve. In fact, our wheels are already on the rumble strip. This is why we need projections to look forward to see what's going to happen so we can plan for it. We know that our weather goes up and down from day to day, month to month, and year to year. We have hot and cold, we have wet and dry, but our planning is built on climate, which is the average of weather over at least 20 to 30 years. What aspect of our lives are built on the assumption that climate is stable? Pretty much everything. Our residential and commercial building codes, what types of crops we grow, where and when and how, whether we have an air conditioner or not, and if so, how big it is. Also the same for a furnace and insulation. Where are the 100 or 500 or 1,000 year flood zones? Whether we invest in snow removal capacity, how much water or energy we're going to be using in the future. Even the clothes in our closet are built on the assumption of climate. I have being from Canada, a Canada Goose jacket. I dragged it all the way to Texas with me. It hangs on a hook where I can admire it. And the one day a year it snows, because it does snow in Texas, I pull it out and I put it on even though it's too warm. Why do I have that jacket? Not because I'm from Texas, because I'm from Canada. Climate determines so many aspects of our lives. But today, climate is changing. We still have hot and cold. We still have wet and dry, but the long-term average is changing. And this matters because it affects planning for what? For infrastructure, resources, health, national security, the economy, agriculture, food, water. But that's not all. We also know that in many cases, our variability is changing too. And that could be even potentially more risky because it takes the risks we already face and it is exacerbating many of them, making them worse. We know that wherever we live, we are subject to droughts, floods, hurricanes, blizzards, ice storms, wildfire, all kinds of other storms and more. And in fact, Texas gets more damaging storms than any other place because we get everything. We get droughts and floods, we get ice storms and heat waves, and we have a lot of infrastructure and things of value to be damaged by them. Wherever we live, we are always subject to the risk of a natural disaster, right? But what climate change is doing is it's sneaking in and loading the dice against us. It's taking one of those numbers and turning it into a 6. And then another number and turning it into a 6. And then another number and turning it into a 7. And all of a sudden we're rolling the double 6s much more frequently than we should be. And we say, how could this be happening? That's climate change. We know that heavy rainfall is becoming more intense and more frequent in a warmer world. We know that heat waves have become more frequent and we still get cold waves, but they're less frequent. We know that wildfires are burning greater area. Most of them in the lower 48 states are human ignition, most accidental human ignition. But once they get started, they're burning a lot more area. And we know that some years we have more hurricanes and some years we have less. But overall, the hurricanes we get are getting bigger and stronger. They're intensifying faster and they have a lot more rainfall associated with them. So when we look to the future, when we look to that curve in the road, it is still a bit foggy because it depends on our choices. We have to know how much we're going to have to adapt to, even if we do our absolute best. And of course, RCP 4.5 is not the lowest scenario. Our absolute best is hopefully going to be below that if we really get our act together. But what we can avoid by prompt action now, we need to know that too. There was a great question during the last panel that said, well, isn't it just cheaper to adapt, right, than to mitigate? This work, and the work that I and others in this field do, actually shows how much adaptation will cost. And what it shows is that for the US to meet its Paris targets is going to cost a certain amount of money. But if the US does not meet its Paris targets, and that means the world in general fails to meet its Paris targets, the price tag for the US is going to be larger than the price tag of actually meeting its commitments over a time scale of anywhere longer than about 10 years. So you might say, well, obviously, why aren't we doing it then? Well, it's because the average political term is less than 10 years. I hate to be frank, but that's probably the biggest reason. So when we look to the future, we have to then ask ourselves, well, which scenario is the right scenario? And this is a question I get a lot. People don't want to waste their time looking at the wrong scenario. Just give us the right scenario. But here's the thing, that curve in the road depends on a lot of question marks. And two of the biggest question marks are, what are humans going to be doing? How much CO2 and methane and other heat trapping gases are we going to produce? Number one. And number two, how is the climate system going to respond to this truly unprecedented experiment that we are conducting with the carbon cycle? Now, don't get me wrong. We know it's been warmer before. But we also know that if we continue, first of all, we know that CO2 levels haven't been this high in 15 million years. So we know that it's never been this warm and it's never been changing this fast over the course of human civilization on this planet. And that's the key, Human civilization is what is at stake here, not the planet itself. The planet will survive. The question is, will we? So CO2 levels are higher than they've been in 15 million years. If we continue on our current pathway, that orange line at the top back there, let me go back there, that will put us at warming levels and CO2 levels that we haven't seen in 55, 60, 65 million years. And we also know, as far as we can from paleoclimate records, although of course there's a lot of uncertainty there, that the amount of carbon that we are putting into the atmosphere on an annual basis is truly unprecedented. Even the times of fastest change in the paleoclimate record, I don't think we've seen any more than about 1/10 of the carbon on average going into the atmosphere, although it's hard to tell, of course, you can't tell on an annual basis, but best estimates are significantly less carbon per year than we're putting in now. So that's why we need these scenarios that capture the relationship between the choices that we make and what those mean for our sources of energy, how much energy we use and where it comes from. And we need these sources because we can't predict human behavior. In fact, here's the interesting thing. By looking at the consequences of our behavior, the point is that we're hoping to actually change it. So if you didn't know that smoking caused lung cancer, would you smoke? I'm pretty sure I would. They say it's good for the nerves, relaxing. If you didn't know that eating trans fats was bad, would you eat more fatty food? You probably would. I would. So knowledge of the outcome of our choices has the ability to modify our behavior. And that's the point of looking at multiple scenarios. So for example, here are the carbon emissions for 2 different future scenarios. One where we continue to depend on fossil fuels, one where we transition fairly rapidly, but not as fast as we could if we really tried, to clean energy. And then if you put these into a climate model, this is just one example, this is the GFDL model, you put this into a climate model and you look at projected changes over the US. Well, right now we don't see a big change because the scenarios don't diverge, right? We're living in them right now. But the further you go out into the future, the bigger the change you see. But here's the thing, by the time you get here, you can't choose which scenario you want. It's too late. It's as if you're being loaded onto the ambulance with a heart attack, going to the hospital for bypass surgery, and you say to the EMT, oh no, I promise I am going to eat much more healthily. I will join a gym. I will exercise. You don't have to take me to the hospital. The EMT just laugh and say, it is too late. Your doctor told you to do that 20, 30 years ago. So the whole point of these projections are we want to look ahead to where we're being loaded into the ambulance, so to speak, and figure out how serious is that? Are we willing to pay that price tag? And if we are not, then now is the time to choose a different pathway. That's the point of the projections. So here are the carbon emissions for a bunch of different scenarios now. You can see we've got a lower one here, RCP 2.6, and the new set of scenarios that came out called SSPs. They combine the RCPs with socioeconomic projections, and they actually have one a bit lower. They have a 1.9 too. Here's the temperature on the other side. You see there's a range of uncertainty because of the response of the climate system to what we're doing to it. Which of these is more likely? We don't know. And in fact, unless you're one of these two people, God, or growing up in the Midwest, you probably know who the middle person is. I went to grad school in Illinois and lived in Indiana for a number of years. This is Miss Cleo. Her ads were always on TV, Miss Cleo the psychic. Unless you're one of these people, and frankly, unless you're really just the one on the left, do not try to pick a most likely scenario because you're not going to be right. We can look at what's happening in the world. We can say, oh, well, greenhouse gas emissions have already peaked. That's good news. But ride-hailing services like Uber and Lyft are increasing carbon emissions. Oh. We find that America's coal consumption is way down, which is great news, and so is China's. But you know what China's doing? They're building hundreds of coal-fired power plants in poorer countries so they can sell their coal to them. Bad news. We know that the coronavirus lockdowns cut carbon emissions temporarily 17% in April, but we also know that methane emissions have skyrocketed. So we're not doing that great. And if you look at the Climate Action Tracker, this is a great website, I highly recommend it. You can see where current policies are You can see the uncertainty range. You can see where we need to go. So we're certainly doing things that are moving us in the right direction, but we're not yet doing enough. So we look at multiple scenarios because the act of observing what could happen to us will actually dynamically alter our future. A little bit, not quite, but similar to Schrodinger's cat. The greatest uncertainty when it comes to the future is us. So part 4. And as we go along, you can put questions anytime if you're watching this live in pollev.com/Katharine. Go to the chat, the link's right there. Go ahead and put your questions there, and you can look at other people's questions and upvote them as we go along. If you're not watching this live, I'm sorry, the window has closed, but we will be answering questions at the end. All right, so part 4 then. How do we show the impact of these choices? What do we do? Well, we have to model the future because we don't have a crystal ball. And even if we did, I don't think it would be accurate. So how do we actually model the response of the climate system to this unprecedented experiment we're conducting with it? We need to look at the feedbacks in the climate system. That's why it's uncertain. We've known the radiative impact of adding more CO2 to the atmosphere since the 1800s. The direct radiative impact of more CO2 is not rocket science. We've known it again for over 100 years. What is really difficult, though, are the feedbacks or self-amplifying cycles in the climate system. How will clouds respond? How will Arctic sea ice respond? How will the permafrost with all the methane and carbon trapped in it respond? How will ocean currents respond? And how will these amplify, because yes, the net effect is an amplification, how will these amplify the net effect of the CO2? It's likely that it increases it by at least 50% and possibly more. So this is why we need the models to look at climate sensitivity. And climate models, as many of you know, they're not just based on statistics of correlations between warming and CO2. No, they're based on fundamental physics. There's hundreds of mathematical equations to represent the atmosphere, the ocean, the biosphere, the hydrosphere, rivers and lakes, the cryosphere, frozen water, and even increasingly, people are starting to add levels of soil too in geologic activity. And we need to have all these different pieces in the models because moisture, water, energy, mass all flows between different parts of the climate system. Now, this is sort of tongue-in-cheek, a simple diagram of the physics that goes into at least the atmospheric part of a climate model. You can see that it is not just straight up correlations. It is very complex. Now, of course, anybody who's ever spoken about models knows we can hardly even give a presentation without mentioning this famous quote from the statistician George Box: all models are wrong, but some are useful. And those of us who study models spend all of our time trying to figure out what's wrong with them so we can improve them. I'll show you a little bit of that next. But what we do know is that over time, these models have become more and more useful. Why? Because we're adding more and more components to them, and we're testing them against real world information, both in the distant past, as well as today, and even on other planets. Yes, people use climate models to model Venus, Mars, even Jupiter. So how do these models work? They divide the world up into smaller and smaller grids: the ocean, the atmosphere, the land surface, the ice. And it lets us do experiments with the planet because unlike other types of scientists, we can't just put the Earth in a test tube in the lab. So our models are our lab. And I always laugh when somebody says, I want to see your lab, because my lab is actually the High Performance Computing Center. And I never go there in person unless there's somebody who wants to take a picture of it, because you just connect remotely, right? So our lab is these models, and we use thousands of lines of code, some of it's still written in Fortran since they're very old, and we put them into some of the most powerful supercomputers in the world. This is a cartoon from GFDL, not a real picture. And we have dozens of these models. And what these models are they're best envisioned as a different Earth, one that has the same continents as ours, one where we can put in the same forcing as ours from volcanoes and the sun and human emissions. but different Earths that have different patterns of natural variability. And this is really important because natural variability is chaotic. And the reason why there's different patterns of natural variability is why when you look at climate model output, you see a range. So what you're looking at here, the black line is the observed global temperature from 1850 until, I think this one goes to 2019. So the black line is observed global temperature, and then the shaded area is the multi-model ensemble from CMIP 5. I haven't got CMIP 6 out quite yet because it's still being completed. And you see a shaded range because the natural variability on each planet differs a bit. One planet might be having an El Nino, while the other planet is neutral, and the real world is a La Nina. That doesn't mean there's anything wrong with it. It just means that natural variability is chaotic, and so the models have their own patterns of natural variability. At the local scale, this becomes even more important. Let me show you. These are some simulations that we did for Wilmington, Delaware, for example. The black line is the real temperature from 1960 to 2010 at the weather station. So we're super local now. We've gone from global to a single weather station. Then the different colored lines are different climate models that have been downscaled to that weather station. And I'll explain what downscaling is next. But what you can see is that you might look at this, you might say, oh, none of these models look like reality. Well, they're not supposed to. What they are supposed to do is they are supposed to capture the observed range, which they do, and they're supposed to capture the long-term climate trend over 20 to 30 years, which they also do. That's what models are supposed to do. So that's why when we use climate projections, we need to make sure that we average them over climate timescales. And there's no one perfect global model, but it turns out, and this is a paraphrase of many scientific papers, if we use a lot of them, we're likely closer to reality than picking out a single one. Sometimes we can identify a reason why a model doesn't or shouldn't be used for a certain area if it can't simulate sea ice, for example, in the Arctic. But increasingly, most models get most large-scale dynamic features. We have to use multiple scenarios to ask if-then questions. If we do this, then what will happen versus if we do this, what will happen? And we have to remember that there's always the potential for surprise. And in fact, most of them are likely not going to be good. So that alone gives us reason to take this very seriously. All right, part 5. Now, for those of you counting, we're going up to part 6, and then I'm taking your questions. So go ahead and put questions in polev.com/Katharine if you want to, and we'll get to questions at the end. Part 5. What do we use these climate projections for in real life? Well, this is where we get interesting. So first of all, we can put them in the test tube, so to speak, and we can look at what would happen if the Earth was only being affected by volcanoes, or only being affected by the sun, or only being affected by changes in land use, or only being affected by greenhouse gases. And then we can divide out all these different factors and see how they're influencing what's happening. And we can put them all together and see that, you know what, we do understand why the Earth is warming. It's mostly human. In fact, the natural forces are helping us out. We can also develop future projections, and these figures are all from the National Climate Assessment from Chapter 2, which I was the lead author on. We can look at what will happen in the future under a higher scenario versus a lower scenario, right? By mid-century and by end of century. And most importantly, and this is what I do, we can downscale it to individual weather stations or high resolution grids, so we can actually see what the two different scenarios mean for the places where we live. What is downscaling and why do we need it? Well, I get into it a lot more in this chapter I wrote for the National Climate Assessment, Chapter 4. So if you want more information, go to Chapter 4 here. But basically, global models don't give us the spatial or temporal resolution that we need, and they also don't even give us the variables that we often need. People are often more interested in, how many days above or below freezing. Well, that's not an output. An output is maximum and minimum temperature. So you have to calculate a secondary variable. Or people might be interested in something like how often do we exceed the 100-year flood zone precipitation. So then you have to look at that too, and you have to incorporate land surface modeling into that. Climate model outputs usually need to be downscaled and translated, and there's a lot of different approaches, and there's no one best approach, just like there's no one best climate model. Which one is best often depends on what we're doing, what we're using it for, and what our resources look like. So for example, you can downscale using regional climate models. So those are like just a square rectangular area over a much smaller place. And at the boundaries, you use the global model output at the boundaries. And then you just model, the state of Ohio or the Great Lakes region at much higher resolution. Or you can use statistical models, which are a lot faster. They're a lot more computationally efficient. They automatically bias correct the outputs. So you actually get numbers that look like the observations. But you don't have that dynamic simulation going in at the fine scale, and you require observations to run a statistical model. Because with a statistical model, you develop a relationship between observations and the global climate model, and then you use that to downscale the future projections. Whereas regional climate models, you can use even where you don't have observations. So places like the remote Arctic, places like Africa, where the whole continent has about the same number of long-term weather stations as the state of Texas, that's where regional models really come into their own. So if I'm working in an area, a geographic area, with few observations, or if I need a lot of different variables like cloudiness, soil moisture, solar radiation, wind, I would definitely use a regional climate model for that. But if I'm working in an area that has a lot of observations, and I typically just want temperature and precipitation, and I want to have a lot of climate models for a lot of different scenarios, so I really capture the uncertainty, then I typically use an empirical statistical model. What's the difference between using one versus the other? This is what my research addresses. And I just want to give you a small kind of vignette about it because I find my research personally very fascinating, and I hope that you might too. So what we've done is we've actually, with colleagues at GFDL, we've developed a method to test statistical models. Our method is to have a super high resolution 25-kilometer global model for the future. And then we have a coarse global model for the future. And we train the downscaling method on the observed period, the historical period. And then we downscale to the future, and then we compare it with the super high resolution global model, and we see what's lost. What's the difference? Now, of course, we don't actually have reality for the end of the century. Check back with me in 80 more years, and we'll be able to have reality. I don't think I'll be doing this in 80 more years. I probably won't be here. But this is the best that we have now. So what we did, for example, is we coded up 3 common statistical downscaling approaches. The one that we originally developed and that we asked Matt to optimize for us in R, that's the one on the left. We developed that one back in 2012. And then a simple delta method that a lot of ecologists use, and a quantile mapping method that a lot of hydrologists use. So the one we did, the ecologist one, the hydrologist one. And then we looked at what do you lose by using this method as opposed to a super high resolution dynamical model. And it turns out that for the coldest day in 1,000 days, that's the top level, and the hottest day in 1,000 days, that's the bottom level, you can get biases in temperature anywhere from 1 or 2 degrees up to as much as 10 degrees bias in temperature. And this is in degrees Celsius, not Fahrenheit, Celsius. So you can get anywhere from 1 or 2 degree biases up to 10 degree biases. And we were fascinated to see that our biases in our model were along the coast, because we weren't accounting for the way that the land sea breeze would be changing in the future as the land warmed faster than the ocean. Isn't that interesting? Then we looked at precipitation, we looked at the global scale. So you can see these global patterns of biases too. And then we looked at precipitation. And guess what? Remember I said the one on the right is used by who? By hydrologists. Well, it turns out that method is genius for doing precipitation. It is fantastic for doing precipitation up to the most extreme precipitation. Now, at the most extreme precipitation, the wheels fall off the bus and you get about a 60 to 90% bias in too much precipitation. But there you're talking about the wettest day in 1,000 wet days. That's not the wettest day in 1,000 days. It's the wettest day in 1,000 wet days. So that's way, way to the tails of the distribution. And if you're doing hydrology, you typically care more about precipitation over timescales of weeks and months than you do of 1 day in 10 years. So it turned out that the hydrology method is absolutely fantastic for doing hydrology, which is awesome. And then it turned out the delta method, which is actually quite good for temperature, which is what drives a lot of ecology, it was very good for temperature, but it was not so good for precipitation. So then the wheels started turning and we thought to ourselves, okay, what if we designed a brand new downscaling method within this framework where we could test it at every step of the road? What if we did that? So at the global scale, here's the 3 methods we already tested. And then we developed a brand new one, and it's taken us 5 years to develop this brand new one. And what does it look like? This. Yes. Because every step of the way we stopped, we looked at the physical processes that were causing biases, and we thought, what could we do to accurately account for how these change in the future? But even this model is not perfect, and it should never be perfect. If you have a perfect model, you should be very suspicious. It's not perfect. And when we zoom in and we change the scale, so instead of going from -10 to +10, we zoom in and we make the scale much finer, we see that we still have problems. So at the time we were developing this, we were working in India. And we knew that our old method had really big biases, not only along the coastline, but also over the Himalayas. And it turned out that our new method mostly got rid of the biases along the coastline. And again, note the scale down here. The scale is from 5 to 5 now instead of 10 to 10. It got rid of the biases along the coastline, but it did nothing about what was happening in the Himalayas. Well, it turns out we dug into this and we plotted the bias by month. All of the bias comes from 1 month. It comes from a single month. What month do you think that is? It is the month of peak snow melt in the Hindu Kush. That happens to be July there, and in the Rockies, it happens to be April. So we see the same thing in the Rockies at high elevation. So in other words, we were using statistical relationships developed for being over snow for a month in the future when there wasn't any snow left in July anymore at those elevations. So by shifting our statistical relationship, then we could actually start to improve our simulations at higher elevations too. So what are we doing? Well, we are downscaling weather stations and we're downscaling grids for Canada and the US, and we're hoping to go global next year. But so far we've done about 10,000 weather stations across the US, and we've done a 1/16th degree grid across the US, and we're going to be working soon on a 5-kilometer grid across the US. In Ohio, this is what the weather stations look like that we have. You can see some of them are a little questionable there sitting in Lake Erie. Going to have to look at those locations on our map. And we've even done a few simulations, like how do we expect the temperature of the hottest day of the year to change in the future under a higher scenario? It's just looping through here from the 1980s or 1950s to the end of the century. And simulations of how many days per year are going to be exceeding the average hottest day of the year from the 1950s to the 2000s. You can see this balloons up very quickly. So we're going to be doing this type of calculation as well. And then lastly, we can use this information. Now, again, get your questions ready because we'll go to questions next. But I can't end without circling back to where we began. Why do we need this information? Because we need to look at the outcome of our choices. Why? Because we need to understand that climate change is not distant. It is here and it is now, and it is affecting decisions that we make today. So this type of information can be used to inform mitigation. In other words, by illustrating the difference between a higher versus a lower scenario, you can actually say, we want to reduce our emissions because the higher scenario is too expensive. The city of Chicago came to this conclusion after we developed projections for them. The state of California under Governor Schwarzenegger at that time came to that conclusion. And in the executive order he signed that made California the first state in the country to have mandatory greenhouse gas emission reductions, it literally said, because we don't want the impacts of the higher scenario, this is why we're reducing our emissions. But this information can also be used for adaptation, because even if we mitigate, we're still going to have to adapt. It's no longer a choice of which one we want to do. The question is only how much. The more we reduce our emissions, the less adaptation is required. So how do we figure out what to do with this information? Step one, what do we care about? And that doesn't start with the climate scientists. It starts with you. It starts with stakeholders. Do you care about fish? Do you care about drought? Do you care about invasive species? Do you care about algae? What do you care about? And then step 2 is, how does that connect to climate? Invasive species often relate to cold winter temperatures that keep them at bay, or that are not keeping them at bay these days, I should say. Flooding relates to rainfall, right? Wildfire relates to the dryness of the vegetation over longer periods of time. How does it relate to climate? And for some purposes, we can stop right here because we know enough about the vulnerability of our system and the fact that it's going in this direction to build resilience into future planning. We don't need quantitative projections. For some other purposes, we just need to know, how is it changing roughly? And for how is it changing roughly, we have information. We have information from the National Climate Assessment Volume 1 that goes through temperature, precipitation, storms, sea level, Arctic, all of that. We have information from Volume 2, which goes through every sector and every region. And for a lot of applications, this is enough to make smart choices, because let me give you an example. So say that you are concerned about extreme heat in Columbus. And we could develop projections of how much more extreme heat you're going to be getting in the future. And we've done this. But what are your adaptation options? Your adaptation options are install a heat watch warning system, create cooling centers, create rebates on people's bills so they don't have to pay their air conditioning during a heat wave, create social networks where people call each other or check in on each other, especially in vulnerable populations, to make sure they're okay. Would you do any of these differently if I told you heat waves were going to be 5 times more frequent or 6 times more frequent? No, you wouldn't do it differently. So in that case, having the quantitative projections might not be so important, although maybe even to do something, you need to have some information, but your adaptation options are pretty much the same. Now, let me give you an example where they're different. You're redoing your sewage or your storm sewer pipes. We lived in South Bend for many years. We had an old house. If it rained, we had to drop everything. If we were in the movie theater, I was like, oh my gosh, is that rain? We would leave the movie theater to run. We would run home. We would run down the basement. We would yank up an old iron lid. We would reach down 2 feet. We would turn this rusted old 100-year-old wheel to close off our house from the storm sewer system. Now you might say, why the heck didn't you just buy one of those flaps? It's because they cost $800 and we were just out of grad school and we didn't have the money. But believe me, we found the money because, well, we did that. The first summer we went home, I went home to Canada for the summer, and we left a graduate student house sitting our house. We warned him about running home and turning this, but he didn't quite get the urgency of it. So the first time he came home after a major rainfall, there were 4 feet of raw sewage floating in our basement. Yes, thank goodness for Allstate. Allstate has given us more than we have given them, I think. So anyways, if you're replacing your storm sewer system, you need to know how big new pipes to put in, because the pipes are going to last hopefully 80 years, right? Or more. So you need to know, you don't want to put in 2 big ones because that would cost too much right now. But you don't want to put in 2 small ones because digging them up and replacing them in 30 years is going to be more expensive. So that's an example where high resolution quantitative information could help. So back to where we were. So for other impacts, we do need this quantitative information because the future is uncertain. But what we know for sure is that if we use the past as a guide to the future, you're going to get the wrong answer. So how do we make sure this information is useful? I found that it's really important for it to be relevant and timely, and it's best if the request from information originates from the stakeholder rather than the scientist, because then they actually want it. So for example, I work with water districts, and after one local water district had a drought, that was when they decided they wanted climate information. Then it's important that there's that reliability factor. There's a lot of people who, if it comes from OSU, will be a lot more trusting of it than if it came from like UC Berkeley or Columbia University. I found the same here in Texas. Working with the water district, they cared because the senior hydrologist from an engineering company that they trusted was vouching for the information. And when they introduced me, it wasn't about me and what I accomplished, it was about Texas Tech. That's who they trusted, was the university. Now, I might be a climate scientist, which was a bit sketchy, but at least I came from the university that they trusted. And then lastly, we need to make sure it's correlational, or rather co-relational. We're meeting people where they're at, not where they want to be. In Texas, this is the study area that we had. And in Texas, you can see that most people in that area would not agree that global warming is mostly human caused. We're kind of looking by Dallas, Fort Worth, just up and a little bit to the side of it. But most of them agree that it's happening. And most of them agree, even more of them agree, it will harm people in the US. So I didn't force people to agree that it was humans causing climate change. We just showed them what was going to happen in the future. And people are like, okay, the data is the data. They literally said that. They said the data is the data. You know, my kids come home from school and tell me that the polar bears are in danger, and I don't believe that, but the data is the data. And so they're making decisions based on climate data. So here's the bottom line. Here's why I do what I do. The future is uncertain, but we know enough to act now, because we are all in a giant bus hurtling down this road, heading towards the curve with the concrete grain silos. And to make it around that curve, we have to mitigate and we have to adapt to ensure a safe future for us all. Thank you.
Thank you so much, Katharine. So I guess we'll go on to the questions that are popping up on your poll EV.
Yes, you guys have been great. There's tons of questions here, which is fantastic. What are the biggest data gaps and issues that need to be solved to further improve climate models? This is very near and dear to my heart. So we have realized in recent years that really making sure that we capture the envelope of natural variability through multiple simulations is really important. Computer model simulations are very expensive. And so traditionally we haven't done that many of them with each model, but we're starting to recognize we need to really make sure we capture the full envelope, because the black swan events, the rare events, the extreme events, those are potentially the most damaging. And if we don't have a good handle on natural variability and how it's being affected by a changing climate, we might seriously underestimate those risks. We're also concerned about what's happening at the poles. What is happening to Greenland and Antarctica? For years, the global models have not been able to do a good job simulating what is happening under a mile of ice. And that's why research like OSU does is so key. Why? Not because that many of us live in Greenland and nobody lives permanently in Antarctica, but it's because that's the reason why sea level rise is accelerating. Greenland is melting, I think something like what, 6 times faster than it was in the 1990s? We have 700 million people who live in the low elevation zone around the world, including 2/3 of the world's biggest cities. So understanding what is driving sea level melt or sea level rise and how fast it's happening is key. Then we've got the issue of the soils, which Fred Yoder discussed so eloquently in the panel just before, how soils can be both part of the solution to climate change by taking up carbon through smart management and afforestation and protection, but they could also potentially be part of the problem, especially in the Arctic, where soils are melting, permafrost is melting, releasing carbon and methane into the environment, into the atmosphere. So understanding what's under our feet is really important. Understanding natural variability is key. Understanding what's happening at the poles is really important. And of course, clouds are the perennial uncertainty as well in the climate system, because you're trying to model microphysical processes at 50 kilometer, 100 kilometer resolution. So there's a lot to be done, but again, we know enough to act now. For wildfires, forest management, yes. For wildfires, climate change is not driving more of them, it's making them worse. And forest management can definitely play into that through smart burns. I don't know if you're familiar with Project Drawdown. I mentioned it earlier in my previous presentation, but they have a lot of good resources that talk about how indigenous forest management and other smart forest management techniques can sequester carbon as well as reducing the impact of wildfire. But again, climate change, what it's doing is it's loading the dice against us by drying out the vegetation. So even if you manage the forest, you still have tinder dry, sorry, probably bad choice of word, bone dry, kindling. And you have beetles that are overwintering due to warm winters, eating millions of acres of trees. So climate change really is a threat multiplier when it comes to wildfires. This is a question near and dear to my heart. As a science communicator, I often get questions about scientific uncertainty. Does it invalidate our science? I'm just going to go ahead and put myself up here so I can see you and then keep talking about the questions. I love this topic because here's the thing. As scientists, we are trained to talk about what we don't know, right? If you go to an AGU presentation or an AMS presentation or GSA or an ESA or any scientific conference, right? The presentation is one slide about what we knew before, and then the whole rest of the presentation is what we just found out just now, with lots of uncertainty bars on it. And then the last slide is what we don't know yet and what we still want to find out. Because the whole reason we're scientists is that curiosity. We want to figure stuff out. So we are trained to talk 99% about what we don't know or we just found out, and 1% about what we've known for a long time, because that's not so interesting to us. Here's the thing. When you're talking to the public, you got to flip it. Flip it. 99%, we know climate is changing, and we've known that since Guy Calendar in the 1938. We know why it's changing, because humans are digging up and burning fossil fuels. That's 75% of the problem, and 25% is land use change, deforestation, and agriculture. We know that. We know that the impacts are serious. We know the time to act is now. We know our choices can make a difference. Scientists warned a US president 55 years ago of these 4 things. So when we talk to people, 99% of what we say has to be, we know this. And then the 1% uncertainty is, you know what? We are conducting an unprecedented experiment with the only home that we have. Shouldn't we be taking more care, especially because we humans are the biggest uncertainty in the climate system? There is uncertainty, and that actually makes us even more worried about it, not less. It is so important to talk about it like that, to acknowledge there is uncertainty, but to show that uncertainty actually makes us more worried, not less worried about what's coming in the future. My sort of favorite / least favorite chapter of the National Climate Assessment is chapter 15 of volume 1. It's called Potential Surprises, and it talks all about what we know that we don't know and how none of it is good. So if you think that uncertainty is reassuring, or if you hear people saying that uncertainty is reassuring, just go to chapter 15 of, I'm going to type it in here, science2017.globalchange.gov. Go to chapter 15, read that, and you will no longer believe that uncertainty is reassuring. It will scare the pants off you like it does me. All right, metaphorically. Okay, we have a couple more minutes, so let me go through a few more questions, because these are great questions. It seems like you're saying that climate change is the cause of whatever problem we want it to be. I'm very glad you asked that, because my answer to that is no. I am not saying that climate change is the cause of pretty much any of our problems. Let me repeat that. Climate change is not the cause of most of our problems. It's not. What is it? It is, as the US military calls it, a threat multiplier. What is a threat multiplier? It's something that takes an issue like what? Poverty. Climate change has already increased the gap between the richest and poorest countries in the world by 25% since 1960. Hunger. On average, the world has been losing $5 billion worth of crop losses, most of that in developing countries, every year since 1980. Political instability. Climate change actually drives conflict in resource-scarce areas, not stable countries, but countries that are already on the edge politically already. Climate change exacerbates those. Climate change affects other issues like our health. It intersects with environmental justice, issues of racism. Women and children are disproportionately affected by climate change. Indigenous peoples are disproportionately affected. Everybody who's already vulnerable to other pressures and other stresses, most of those people, even people who are disabled, for example, are disproportionately affected by changing climate. Climate change is not igniting the wildfires. Once they're ignited, they burn more area. Climate change is not causing hurricanes to form. Once they form, they intensify faster and they have a lot more rain associated with them. Climate change is not causing poverty. Climate change is not causing hunger. Climate change is not causing resource shortages. It is taking things that already exist and it is exacerbating them or making them worse. Thank you so much for that question. To be honest, I think that is my favorite question. I'm so glad that I got a chance to expand on that. All right, we have time for a couple more questions in the speed round, and then do not disappear because we have a short break and then we have a great panel. Please stick with us for the panel, okay? Grab your lunch and come back. But speed round here, last few questions. complexity in models can result in diminishing returns. Have we started to see that? Yes and no. We already know climate is changing, humans are responsible, our choices matter, and the time to act is now. So new fancy climate models aren't going to tell us that. But understanding how they're affecting us, the property values in Florida, crop yields in the Midwest, area burned by wildfires in Australia and Alaska and the Western US and Canada, that's where climate change can really help us put information and numbers on it. And one of my favorite new books that I encourage you to check out is called Angry Weather. It talks about the emerging science of detection and attribution. And it is a great book. I'm going to drop a link in the chat right here. I highly recommend checking it out because it talks about the cutting edge of what we found out now that we didn't know 10 years ago about attributing climate change. And it is a stunner. Do not miss Angry Weather. All right. How do climate models of the past compare with the current state of the Earth? I love this because Carbon Brief has done a really good comparison of climate models from the 1970s through now, and they do a fantastic job. Let me drop that in the chat right here. If you want to know how climate models have done, check out there and you'll see from the 1970s to now, they have tracked the observed temperature incredibly well. Let's see. What academic fields have the greatest opportunity to reimagine their subject area? Oh my gosh, everybody. Yes, I work with, and I'm not kidding, I work with people in English. I work with people in psychology. I work with people in education, in public relations, in ecology, biology, chemistry, physics, obviously, economics, petroleum engineering, political science. Every single discipline has something to offer. Artists have something to offer. Social scientists, humanities, engineering, architecture, law, medicine, business. Everybody has something to offer. And so my favorite thing is when I hear somebody from an unexpected field doing something really awesome, that's the person we need. At our Climate Center here at Texas Tech, we have 56 faculty affiliates from every college across the whole university, including health, public health, architecture, law, art, music, design. We need everybody on board because climate change is not a science issue. It's not just an environmental issue. Climate change, and I think this is a good point to end on, climate change is a human issue. And to care about it, we only have to be one thing, and that is a human living on this planet. And as far as I know, we're all that. Thank you.
Great. Thank you so much, Katharine. That was just an amazing talk and great information to pass on to us. And as everybody can see, the discussion is getting nerdier and nerdier as the day goes on, which is wonderful. So as she mentioned, we'll take a short break now and we'll reconvene with our science discussion panel at 1:10 p.m. So you have a short, 8 or so minute break, and we'll talk to you soon. And so we have our really amazing panel lined up here to discuss the science. 5 professors, scientists here at OSU, covering a wide range of fields. So that's really interesting to provide their perspectives, maybe in the context of their research and following up with Katharine's talk. So I'll just briefly introduce them and then they'll have 5 minutes each to sort of maybe make some general statements about their work. And then we'll open it up to the general Q&A. And as in the morning session, you can use the Q&A box on Zoom to enter questions as we go along. So Dr. Bryan Mark is a professor in the Department of Geography, PI at the Bird Polar and Climate Research Center, and the acting state climatologist in the State Climate Office of Ohio. Bryan conducts interdisciplinary research on processes related to climate and water, often in the developing world and or near glaciers. Dr. Stephen Quiring is a professor of atmospheric sciences program in the Department of Geography and a fellow at the Risk Institute at the Fisher College of Business, as well as a member of the TDA Institute and the Sustainability Institute here at Ohio State. And his research focuses on hydroclimatology, weather data analytics, and modeling the impact of storms on electrical infrastructure. Dr. Jeff Bielicki runs the Energy Sustainability Research Laboratory and is the co-lead for sustainable energy at the Sustainability Institute, where he is an associate professor with joint appointments in the Department of Civil, Environmental, and Geodetic Engineering and in the John Glenn College of Public Affairs. His research focuses on the interaction of energy, environmental systems, and policy. Cinnamon Carlarne is the Associate Dean for Faculty and Intellectual Life and the Alumni Society Designated Professor of Law at the Moritz College of Law. And her research focuses on the evolution of systems of domestic and international environmental law. And finally, Robyn Wilson is a professor in the School of Environment and National Resources and the incoming president of the Society for Risk Analysis and a member of the National Academics Board on Environmental Change in Society. And her research is, she's a behavioral scientist focusing on individual decisions under risk. So with that, we will start off with Dr. Bryan Mark. Take it away, Bryan.
All right, thank you very much. What a great talk. Thank you, Dr. Hayhoe. And Matt, thanks for the brief intro. What I want to basically suggest is that models definitely are useful and wrong. I follow that up in my Geography 3900 class, where I try to bring this point home to people that are maybe not thinking quantitatively because they're taking my class to get rid of some GE credit, and it's a natural science class. But I really think that we've ditched a lot of our critical thinking when we throw away quantitative approaches. And so I try to bring us back to some fundamental principles of radiation balance and build the greenhouse model and go from there. But I do also want to bring people back to the point that climate impacts us all, and it's maybe better sometimes to share a story. So for me, you can see the backdrop is a Peruvian landscape where my research takes me to think about glacier change over multiple timescales, to think about what drives those changes climatically, but also what are the impacts. And in the foreground, you see lots of human modified landscapes that are also just imprinted by glaciers that have been on this landscape for thousands of years, but so have the people. And you can also see mine wastes. And so the question now is, if we lose these glaciers as a reservoir of water, what's the impact to water resources? And this is an incredibly integrated and complex story, just like most of what we're talking about. And so models can be very helpful in this domain, but they don't do the full justice to the situation where we really have to talk to people. So this has implicated a lot of social interactions. I also wear the hat as state climatologist for Ohio. And I think in this regard, thinking about ways in which we use model output is really important. I would draw your attention to our webpage where you can learn a little bit more about data sets that we have accessible. And our mission is pretty simple. We just want to get information to people in a format that's more useful to them. And so there's a lot of information out there. And we'd really think that it should be the Ohio State University that retains this position. But if it's not, we'll look elsewhere. But I think it's important to reach stakeholders. And this is where Aaron Wilson, who's on the last panel, is our outspoken spokesperson and climate specialist, reaching out to the ag community as the climate specialist for extension. And so, you know, if this is where also I think we could do a revision as instructors and educators to think about what climate change means. And so we're working on trying to think about ways to get people better educated with maybe a certificate program. These are just a couple of the things that come to my mind. I don't want to speak much longer because we've got a lot of people to talk in this panel, but thank you again for a wonderful talk. And I really look forward to our discussion. And I'll send you that link right now in the chat.
Good afternoon. I'd just like to thank the organizers for putting together the presentations today, and thank Katharine for her excellent talk. I think that as a climatologist and climate scientist, I have much to learn when it comes to effectively communicating complex subject matter to a broad audience, and Katharine's definitely a leader and does an excellent job of breaking down complex material. So my research focuses on hydroclimate and also weather data analytics. And these are two topics where the impacts of climate change in Ohio are quite pronounced. And we can see both in terms of recent drought events within the state, as well as when we think about flooding. And so both ends of hydroclimatic extremes are important and potential areas that the state of Ohio will see major impacts in the future, regardless of which sector we're considering. My work in particular focuses on looking at land-atmosphere interactions. So this is one of the points that Katharine made when we're thinking about improving global climate models. We want to make sure that we have the feedbacks and processes right in those models. So how do fluxes of energy and water from the land surface influence and feedback on intensifying either when we have dry soil conditions, prolonging and initiating drought events, or when we have wet soil conditions, locally enhancing evaporation and transpiration, and therefore leading to even greater precipitation events in the future. The other area that I work is in using weather and climate information to support decision-making. And so this is in concert with Bryan Mark and the State Climate Office, as well as with other organizations and companies within Ohio. And so I think it's important to stress that there is a lot of activity, whether we're thinking about the US military or whether we're thinking about major Fortune 500 companies that are already utilizing climate change projections in their future planning. And so they want to ensure that if they're a company, that their facilities are secure in the future to increased frequency of flooding or other extreme events. They want to generate forecasts in terms of how it will affect their business and what kinds of areas they should invest in. And so if some of the largest and most advanced companies and the US military are already active in this space, this emphasizes the fact that even though uncertainty exists, as Katharine articulated, that we really know a lot, and we know a lot that can help us make decisions now and prepare, even though we don't have a perfect prediction of the future. And so we shouldn't allow that to paralyze us and to prevent us from taking tangible actions today and utilizing all of the tools that we have. And that all models are wrong, but some are useful is extremely important. When we're producing predictions of the impact of a hurricane on a power system, we don't know exactly where that hurricane is going to be, but we can provide actionable information to support preparation in advance of the hurricane making landfall, and also long-term resilience. And that's the kind of role that I enjoy playing as a climatologist, is helping to provide weather and climate information to the people who need it at the spatial and temporal scales that they need to make decisions. And so with that, I will pass it along to Jeff.
Hello, everybody. It's a pleasure to be here, and I've been watching and listening all day, and this has been a great dialogue. I have a bunch of comments and thoughts that have been stimulated in part by the presentations and the questions and answers. But I want to start out with, we kind of have three choices, and I'm going to borrow some framing from my PhD advisor. We have the opportunity to mitigate, we have the opportunity to adapt, and we have the opportunity to suffer. And we're doing each of those now, where what we can't mitigate, we either adapt to and suffer from, and what we can't adapt or mitigate, we are suffering. And this is part of the larger context in which we have concerns. And as Katharine mentioned, the Earth will go on without us. It's whether or not we'll still be on it as a species. I used to work at a couple of Department of Energy national laboratories, and one of my colleagues there said at one point that mitigation is an adaptation to an expectation. And the scenarios and the projections, the climate scenarios and projections that Katharine spoke about are really about establishing these expectations of how the climate envelope in which we live and to which we are adapted may evolve. I like to think of models as they're not perfect. we try to get them more right than wrong. And over time, as we figure out more and learn more, we try to shift the fulcrum from the spectrum between right and wrong more towards that right side. And as we learn more, we keep shifting that fulcrum towards more right. Is there uncertainty? Yes, there is definitely uncertainty in them. But if you, I'm going to make a slightly different anecdote or analogy than what Katharine said. If you're driving along on a road at night in a car, you've got your lights on, it's a little bit foggy, and you know that there is a cliff up ahead. What is the prudent thing to do? The prudent thing to do is to slow down. The fog is this realm of uncertainty, but we know something dangerous is ahead, so we should slow down and try and change what we're doing. The infrastructure we have today is inadequate for the world that we are entering. That infrastructure, the power plants, the roads, the transmission and distribution systems were built over the past handful of decades, and what we build today will last for another handful of decades. And again, as the climate envelope evolves, we need to be able to anticipate that, because the decisions we make today have ramifications for how we can operate in the future. A large part of my research is about turning the carbon dioxide emissions problem into an opportunity by using it to generate renewable energy, more specifically to use it to circulate and pull out geothermal heat. There are two aspects of other work that I've done that I think are quite important here. One of which has to do with Katharine typically December, San Francisco, attend, she mentioned the American Geophysical Union annual meeting or fall meeting. I typically go there, and unlike Katharine, I don't go there from Texas. I typically go there from a cold climate. So I'm walking around in 50 and 60 degree weather in San Francisco, and I'm loving it. I'm wearing a t-shirt. The people that live there, though, tend to be walking around wearing, I've noticed to be walking around wearing warm coats. And so that caused me to wonder if there's a little bit of an acclimation that we have. When I go to a warmer climate, I'm acclimated to a colder one, so I like it. The people who are used to a warmer climate, when they go to the same temperature, they're bundled up a little bit more. And so one of the aspects of the research that I've done is like, can we see this sort of acclimation in our energy demand? And we found that we actually can. We do acclimate slightly to evolving temperatures and meteorological conditions, but that is not by any means enough to does not match the pace at which we project our climate to unfold. Another aspect of the work I've conducted is about precipitation variability and how we need water for our infrastructure, basically power plants. And as you have more variability in precipitation and stream flow, that really affects how we can run our energy system. The final comment I want to make is there's a lot of talk about polarization, and Katharine's earlier talk that she briefly summarized was showed how polarized we are. There was especially about climate, there was a nice article in Daedalus by Rob Sokolow, professor emeritus at Princeton, who was the author 15 years or so ago about the climate wedges. And he talks about witnessing to the middle and trying to find common ground. And we do have examples of this, in particular the Senate, the US Senate just voted to phase out hydrochlorofluorocarbons, and the justification came from two different directions. One is that there's a business case for it, and the other direction is it's environmentally better because they are very poor greenhouse gas emissions. So we can find perhaps overlaps in Venn diagrams where we can agree on a decision, even if we come at it from different perspectives. And with that, I will turn it over to Cinnamon.
Hi, everyone. Thanks so much for having me here. It's a real pleasure. And Katharine, thanks for the fantastic presentation. So a couple of quick points to start with. The first is at the risk of sounding like Justice Scalia and the Massachusetts versus EPA case, I'm not a scientist. I'm not a climate scientist. I'm actually a lawyer, and I have a little bit of background in science, but I am a lawyer by training, and I work on domestic and international environmental law, but primarily on climate change law and have for many years. And I'm grateful to Matt for including me in this conversation because, of course, as Katharine said in her comments, you know, we have a lot of information about climate science, but we still have to figure out what to do with it, both with what we know and with the uncertainties. And in that context, you know, lawyers and policymakers and everybody else are really important. And so opening up the channels of communication and figuring out how to communicate across science and law and policy lines is really, really important. Also, thank you to Katharine for kind of using Texas as a frame of reference, because I will say I am actually a Texan. I grew up in Texas, all my family's in Texas, and you learn very quickly growing up in Texas or working in places like South Carolina how important communication is and how important it is not to lead with what you think is important, but to kind of speak with people about what's important to them. So in Texas, it's, have you noticed that the spring is running, or have you noticed that the spring is drier earlier in the year? Those opening points of communication are really, really important. Now, I'm very mindful of the time and actually watching it pass very quickly. And kind of learning from the era we're in and wanting to listen a lot more than talk. So I'm going to keep my comments very brief. But I just want to say a couple of things. First, a word on kind of scale to just kind of tie into what Katharine's presentation, and then perhaps a word on disasters and inequality if there's time. So the first is I really appreciated and really appreciate all of the work that Katharine is doing thinking about the localized effects of climate change and actually trying to figure out how to better understand and communicate those effects. Recognizing that while they're kind of drawing from Eleanor Ostrom's really important work in this area, while there's no optimal level of response in the climate change context with mitigation or adaptation, it's often really, really important to start at the local level and work our way up. So we're seeing the same thing with law. And the climate change, we've had international climate change law for 3 decades now, and we've tried really hard to develop that framework of international climate change law. And I'm happy to talk about it if people are interested. We've also worked really hard to try to develop something that looks a lot like federal environmental law in the climate change context, and we've had a lot of struggles there. But even as we've seen some failures in that context and some leadership gaps, what you have seen is a tremendous amount of work and really progressive work and effort taking place with respect to local and state level climate change law and policy. And what I will say about that is that there's a tremendous amount of opportunity to do really good work at the local and state level using law and policy to both make substantive changes, both in terms of mitigating climate change, but also adapting to climate change, as we heard, but also for creating lots of opportunities for experimentation and iterative learning about what works and what doesn't work in different contexts, taking into account risk and exposure, but also socioeconomic needs and stakeholder investment. But also there's a tremendous amount of opportunity there to kind of create upward pressure. And so I think that that's really important. I'm happy to talk a little bit more about that if people are interested. And the final thing I want to say is just to really contextualize the conversation about climate change in the context of the world we're living in and the pandemic world we're living in. So interestingly, the pandemic has made us all pay attention all at the same time. The presidents, the prison guards, the UN, the mayors, the great power states, the powerless. It's kind of borderlessness, immediacy, and really kind of merciless morbidity is kind of both frozen us, but also catalyzed us in a particular kind of way. It is a simultaneously globalized and localized disaster. In many ways, it's kind of global climate change and regionalized Ebola wrapped up into one. But it's a disaster that's helping us kind of see natural disasters as not being contained in the local context. I think in this way, it helps us reimagine climate change and to reimagine the possibilities of dramatic change where needed. And one of the other things that I think that the COVID-19 pandemic is really showing us is that, disasters really reveal and exacerbate inequality. And that is something that those of us in the climate change context know and see and think about, as Katharine was talking about, climate change affects women and children and those who are already vulnerable more, and the pandemic does as well. And so it's really, the pandemic is bringing these issues to light. It's showing us how interconnected we are, but it's also showing us the possibility of change. And so even as we kind of learn from and rebuild in the pandemic context, I really hope we can take those lessons and really translate them into the climate change context. Thanks.
All right. Well, hey, everybody. I think I am the wrap-up panelist. I'm Robyn Wilson. I'm a behavioral decision scientist in the School of Environment and Natural Resources. And in my kind of focus area, I think about individual decision-making under risk and uncertainty. So it's a lot of psychology, a little behavioral economics. And I'll just say that as the social scientist on the panel, I really appreciate Katharine doing a great job today. I think really bringing some of that, the state of the science there, into the way that not only she communicates, but her kind of recommendations for how to communicate more effectively about these issues. A lot of my work has focused on how individuals are adapting to climate exacerbated hazards, largely in the context of wildfire and forests, and then also kind of private lands management. And here in the Midwest, it's kind of a flooding and a water quality question. So that's where I find myself focusing a lot on kind of specific climate adaptation challenges. But I think when you look at kind of, what I'd like to speak on just briefly today is just a little bit about the science on the climate adaptation side. We have a much longer history of research on climate communication and even engaging individuals in mitigation compared to thinking about adaptation. And I think part of this was because there was a fear of perhaps engaging communities and individuals in an adaptation conversation, because wouldn't that then perhaps make it seem like we don't have to mitigate? So I think for a while there was some hesitancy to think about that, but I think Katharine pointed this out really well and said the future's uncertain, but the impacts are here and now. We need to mitigate and adapt simultaneously. And just adapting to the worst case scenario is not an economically or a advantageous approach any way you look at it. So, often a few questions kind of come out of that. One is, will a focus on adaptation reduce the need to mitigate? So will you get this kind of blowback or this negative feedback from individuals? And in fact, there was a study in 2014 by Evans and colleagues in global environmental change, and they saw that if you get people to consider adaptation, so think about these kind of local, like Katharine said, impacts that are happening now that are exacerbated by climate, like sea level rise, like hurricanes, like flooding, like wildfire, this actually increased people's willingness to perform personal emissions reducing behaviors. So by having an adaptation conversation, we might even get this positive feedback towards mitigation as well. And when we look at what really influences household level adaptation, again, we have a lot less research in that space and a lot less understanding. But just last year, Linda Stegg, who's a well-known environmental psychologist, she and her lab published a meta-analysis in Nature Climate Change, looking at all of the studies on household adaptation behavior globally, trying to pull out what are some of the key drivers of those adaptation decisions. And their review pointed out a few things. One, we're only looking at a really small picture when we think about the need to adapt to climate change. A lot of our work is on flooding, a little bit on hurricanes and fire, but hardly anyone's looking at drought, heat waves, vector-borne disease. A lot of the studies are also looking on what we might say is incremental adaptation or kind of preparedness behaviors versus thinking about maybe what drives maladaptive actions, maybe thinking about insurance purchasing or policy support. But what they found in that study is recognizing that the focus is largely on flooding and preparedness behaviors. People are more likely to adapt when they see others adapting. We're social creatures, right? And so this is the normative kind of social component. And then two things that I think Katharine also spoke a lot about this morning, that the hazard has to invoke some fear, concern, or worry, but not too much, all right? Because individuals also have to believe in their ability to take effective action. And so there's a few behavioral solutions that come out of that research that are, again, consistent, I think, with what Katharine has talked about today, making the risks local and personal, about the hazard, not climate change itself, while emphasizing perhaps the beneficial actions that others are already taking. And again, I think that's a very consistent message we've heard today. And then the kind of last point I want to make, or maybe second to last, is can behavioral solutions really alter our climate future? So, Katharine made this point, we can't predict behavior, so we need these scenarios. But I would say we can better account for the behavioral uncertainty, just like we account for that kind of physical uncertainty in the climate models. And in fact, 10 years ago, Tom Dietz and colleagues published about this idea of the behavioral wedge and said that we can reduce household emissions by 20% through non-regulatory behavioral interventions. So we do need to think about this, the individual choices and behaviors, both in how we think about mitigating climate, but also adapting. And a more recent study in 2018 by Bielicki and colleagues actually saw that if we bring a better understanding of human behavior into our climate model predictions, future warming could be up to 1.5 degrees Celsius lower. And again, that's actually tied back to people responding to the experience of those climate exacerbated hazards. So the more we can attribute those extreme events to climate change, the more progress we can potentially make. So I'll end with saying I think we still have a lot of work to do. Katharine pointed out our systems are built on the wrong climate future. And colleagues and I just published a paper in Nature Climate Change this year saying we need to move beyond this focus on just incremental adaptation, like what's going to cause someone to put in a window air conditioning unit during a heat wave, which might be good for that individual, but not good for society at large. And we need to think more about this transformative change. So I think we have a lot of work to do to kind of create a society that's more resilient and I guess to the points that several people have made, that ensures that we're here as part of the future and it's not just the planet without us.
Great, thank you so much for all these comments from all the panelists, really wonderful. So anybody who wants to ask a question for the panel, please go ahead and enter your question. This is like the best Q&A session, right? Because you're not a student in the classroom where everybody knows who asks the question, right? So you can ask a question and not be intimidated. And while we're waiting for some questions to come in, I do have some I can ask as well. And so all the panelists, you can turn your cameras on now and we'll just discuss. And of course, if the panelists want to ask questions of the other panelists, please go ahead as well. So one of the first things I wanted to ask is maybe in each of your areas, how important has uncertainty been in terms of maybe interpreting some key results in either your area or your specific research, and especially has it led to any surprises in terms of, the mean might tell you one thing, but then sometimes the uncertainty can be quite shocking depending on the context.
Well, I can just start very briefly, and then allow others to jump in with specificity to say that uncertainty is, very politically manipulatable. And so in the context of law and policy, it's less about often the precision of this uncertainty and more about how that uncertainty is used to push a particular law or policy. I mean, Robyn could probably speak more specifically to how those uncertainties play out at a more precise level when we think about scientific advisory boards and such. But even as those kind of details of uncertainty get manipulated and thought through in the scientific context, it is really, really important how they're presented on the political front, because that can make or break a law or policy, even if we think we know enough to regulate in a particular space.
I would just jump in, and I kind of made this point, but I don't think we're giving ourselves enough credit to try to account for behavioral uncertainty. So our climate scenarios give us this very wide potential future because we don't know how people are going to respond and what those feedbacks will look like. But we do know something about how people respond. So I think we can those bands could be smaller. So we could be better about, and that Bielicki paper I mentioned, which I will drop all of those in the chat as soon as I can. I can't put the PDFs in there, so I got to find the links. But that paper is a great one, and it's one of the few studies I've seen where scientists have really tried to integrate behavioral models to say, we have behavioral uncertainty, we have climate uncertainty, and let's overlap them and see what the future looks like based on our best understanding of both. And so I think we need to do a lot more of that. And it might mean the future looks better than we think. It might mean it looks worse. But I think we need to better account for that piece of the system.
From my perspective, when it comes to uncertainty, we've addressed it in a couple of different ways. One is specifically related to climate change and looking at how well global climate models are able to simulate soil moisture. And so comparing the performance of CMIP-5 versus CMIP-6 with observations over the common period that we have all of those. And we can see that there is progress. And so there was some conversations and questions related to Katharine's presentation about diminishing returns as we go into the future and continue to enhance the complexity global climate models, do we actually see that, does that help give us, does it help reduce uncertainty and give us better information to make decisions? And so in my own work, we see that for the specific case of soil moisture simulation, something that is important for land atmosphere interactions. One of the things I would say as an anecdote, not focused specifically on climate change, but in our work with electrical utilities, is that when we attempt to capture the uncertainty in weather forecasts, so a hurricane's about to make landfall, the power outages in their service territory, depending on which model we use, could range from a lower estimate of this to a higher estimate of that, that the utility often struggles with dealing with that amount of uncertainty. And that even if we can accurately model and capture that, because it's a very large range, because the hurricane could, swerve and change course or get more intense or less intense, that there's also some work to be done. And this is probably squarely in the realm of our social scientist colleagues and Robyn and others, in terms of how we effectively communicate that so it is actionable, decisionable, that it helps inform the decision makers and doesn't paralyze them. And so that, as a climatologist, is a place where I struggle, is that we can quantify and capture and model and represent it all we want, but that may not actually help at the end of the day in terms of providing information that's needed where it's needed.
Jeff or Bryan, did you want to add some comments at all, or?
No, I think those are really valid points. I think one of the ways we're constantly struggling with what we know and what we don't know, especially in data poor regions in the Andes. And so I could give you anecdotes about how we once thought climate behaved in a certain way, given where we thought glaciers were on the landscape at a certain time, but then those totally shrank once we realized we didn't really know the age dates within a reasonable range of estimation. So yeah, uncertainty is something we all deal with. And I think Jeff made a really good point about models getting better over time. And maybe I should emphasize that that's also the case. We improve what we know through that iterative process.
Yeah, I get. Thanks, Bryan. I guess for me, uncertainty falls into my work in a few ways. One is what are the performance? How might facilities or energy systems or whatever perform? How might, and we know that in general, if the temperatures are hotter, power plants are less efficient, right? We know that while there's precipitation variability, how do you plan for the extremes? Do you plan for the mean or the median, or do you plan somewhere around the 80%? And as those distributions are shifting in ways that aren't perfectly knowable, how do you plan for things that you need to rely on for decades? I'd also say that as the models get more sophisticated, there's a lot more opportunities to introduce uncertainties, whether it's how it's parameterized or the relationships for the equations underlying them, or even just the values that are input and the ranges that are input to help run the models. So it's uncertainty is pervasive, but we can typically put some bounds on it and seek to provide conclusions that try to be as robust to the uncertainty as possible, so you have the same solution for the widest range of potential outcomes.
Great, thank you. Here's a question from the attendees. So what are your key recommendations for a local climate action plan? You want to start with Robyn, maybe?
Sorry, I gotta unmute myself. I was actually going to defer to some of our colleagues in bird and geography. And I know we just recently went through that process here in Columbus. And I was kind of hoping maybe they could comment a bit on that plan in particular.
Okay, we could point you again to the climate.osu.edu page and links to the climate adaptation plan that was done for the city of Columbus. And this is an important first step in the direction, but I would say it falls short of a comprehensive strategy going forward. But if you look carefully at that, I think putting into context what Stephen did a nice job articulating to an answer already in the Q&A section, that our future in Ohio looks really to be one of hydroclimatic extremes. So ironically, perhaps we could be facing more floods and more droughts. So how do we think constructively about ways to mitigate and ensure that we have infrastructure in place for those extreme events, those black swans, as Katharine put it, that are not really well constrained by looking in the back, in the rearview mirror at our 50-year, 100-year, 500-year floodplains. If we have scenarios that we really know that are going to be different, we should be playing those out in more constructive ways for infrastructure. But also just putting out from the plan process, what are some of the major concerns that we have collectively once we see the potential scheme of impacts? How do we want to prioritize our resources collectively? And of course, that's the political process, but getting clearly articulated that these are the high priority end members being more resilient against these hydrologic and hydroclimatic extremes, I think are really key.
I just like to hear. Sorry, go ahead, Bryan.
No, I was just going to say, and also we got to, do better than House Bill 6.
Okay, I can definitely agree with that and follow up. Better/opposite. But I just will add here, I want to kind of come back to something that Katharine mentioned earlier. So a lot of my work in the climate change space at both the international level and domestic level focuses on questions of justice and fairness. And thinking about the particular ways in which climate change exacerbates existing inequalities and injustices. And I think even at the local level, it's really, really important to think about that as you're developing local climate plans. Think about, environmental justice and climate justice concerns, the way in which ongoing climate changes, both slow and sudden, will impact communities of color, communities that are otherwise disenfranchised. And I think that that's really, really essential because again, as the pandemic has shown us, disasters exacerbate inequalities, multiple disasters exacerbate inequalities multiply more, right? And so I think even as we start to think about, structurally what can be done to minimize flooding, to respond to flooding, we also just need to think about that like deeply important human aspect.
Okay. Oh.
Just one more plug to think, hopefully, about the co-benefits of a proactive energy economy. We in 2008, with bipartisan majorities, we had all sorts of great innovations and clean energy standards in place, but it was just sort of a wave of ideology that swept through and put a halt to that. So thinking about Ohio and all the unique opportunities we do have and what can benefit across the board, from health to justice to economic benefits of a better energy policy, are key here.
Do you think it really is a wave of ideology, or is there something behind it?
Strongly motivated by certain interests to get the word out. And as we've heard all through today, messaging is so important in our day. We are awash with information, and that's the blessing and a curse before us. So yes, both and.
Great, thank you. So here's another question. Comment on the interplay of responsibilities between scientists, government policymakers, and politicians. Should the role of science change?
I'll jump in. I'm not sure if I'm completely following the question, but the first thought that came to mind is I often speak to our PhD students in this research paradigms class that they take around the role of science versus values, and emphasizing the fact that science and values play two very different roles in the decision-making process. And it is not our job as scientists to tell people what they should do or to identify what is morally right. That is the role of values. What science can do is can come in and say, well, if these are the things you care about, if you do X versus Y versus Z, this is what's going to happen. And that is our role, to link, I think, potential consequences to values, to decision relevant objectives, to goals that people have. And so that is the space that I think we should work in. So should the role of science change? We could do better at that. I mean, I don't think we should start being politicians or decision makers in the sense of making decisions based on what is most values relevant to a constituency, but I think we can do a better job of clearly linking consequences to things that people value, which I think, again, Katharine really made that point this morning, that start on common ground. What is something that people care about, and how can we speak to the impacts on that thing that they care about?
I totally agree with all of that. I mean, I think that there's always ways to improve communication between scientists and policymakers, but I also say that, you know, a lot of that responsibility falls on the shoulders of, you know, policymakers to ask the right questions and to invite the right people. I mean, what we've seen in recent years is, even as policymakers have kind of tried to solicit scientific information, they haven't necessarily gone to those people who are truly kind of working deeply in that space, but more to the high profile names. And so I think that, you know, the burdens and the responsibilities go both ways. And, you know, I always try to communicate to anybody I talk to that, you know, Katharine showed us just how polarized environmental issues and climate change are, and they are that polarized, but they don't have to be, right? And so that's, I think, what all of us are talking about today. We're trying to find ways to kind of make these issues less polarized and to find, you know, points of communication, ways to talk to one another. And I think, you know, scientists can do some of that, but obviously a lot of that burden has to fall on the law and policymakers to be more deliberate, to be more open-minded, to be better at communicating and thinking through who they're talking to, who they're getting their information from, but also what questions they're asking. So of course, we're never going to get good information if we're asking the wrong questions. And so scientists can also help policymakers figure out how to ask better questions.
Yeah, I'll play on that a little bit too. I mean, I think we have to. There's been this notion that it's from science to policy, but it really needs to be an interaction with feedbacks, both asking questions from both sides and answering them and being able to listen. I'll also note that Robyn has a particularly good story about expertise being solicited or unsolicited. And can speak more to the this need for a constant dialogue as opposed to just here you go.
Actually, I'll drop a link in the chat for those that are interested. A colleague of mine who's a political scientist made a little mini documentary on an experience I had with the Science Advisory Board for the EPA for his policy class. But it's very well done, kind of tells the story and talks about science policy and those interactions. So I can drop that in the chat as well if you're curious to hear more about that.
I'm definitely curious to hear more about that and look forward to that video. I would just add that qualitatively, just a reminder that science is a human endeavor. And so when we hear about people like policymakers like Bob Inglis, who is on the right side of the spectrum and came out of the closet in 2009 saying he believed in climate change and voted against the troop surge, it was really, when he talks about this story, it was an encounter with scientists who were passionate about their study and shared a worldview perspective. So I think the way that we do science can be more open and inviting. I think for us, thinking about transdisciplinary approaches, the big challenge is how do we actually frame questions from the outset that bring into account those stakeholder perspectives and questions from the ground up. I don't think I do that very well. So I think there's ways that there's an open invitation and opportunity for ways that we conduct our science that can be more open-ended and lead to better outcomes.
Sorry, I'm just going to make a plug here, which is for the Bird Polar Research Institute. I mean, sorry, I know the title's changed a little bit, but I mean, I actually think that the Institute does an amazing job of opening their doors and inviting people in and providing different methods of communication, better than almost any place I've seen, both in the kind of, they do education online for students, they have tours, and those kinds of things where you really are opening the doors and kind of making science accessible, I just think are incredibly important. And I think it's incredibly important to start at both the kind of the young age education right on up. So I'll say that, you know, that's one of the things at Ohio State that has impressed me is, you know, not only the substantive work being done, but the real effort at communication and kind of open doors.
Okay, great. Well, we're past time, so maybe maybe I'll end with one more of a warm fuzzy question, well, you might answer it not in the warm fuzzy way, but simple one, are you hopeful? So personally, I'm hopeful, worried but hopeful is the way I'd characterize myself.
I'd say with each passing year, when I see the level of interest amongst students and their engagement and commitment to understanding and taking action, that makes me hopeful.
I was going to say I fluctuate wildly from panic to hopeful, and it maybe depends on the day or the week. But I would echo. I think we saw some data today that maybe people's concern or willingness to act on that concern is shifting a little bit as we experience these impacts in more personal ways, and so I think that is happening, and that's hopeful. And then I think even seeing the lack of federal leadership in this space, but seeing other people step up in that void and try to make progress without that is also encouraging. So hopefully all those pieces come together at some point in the near future and we make the progress we need at all scales. But yeah, again, that might be why I fluctuate back and forth.
I'd say I'm we're all fighting for screen time here. I'd say I'm quite hopeful. In the same ways that Stephen and Robyn mentioned, but also from the fact that what we can do today, we couldn't do 10 or 20 years ago. From, for example, the cost of electricity from wind and solar is, only a few cents per megawatt hour, a few cents per kilowatt hour. Wish it was a few cents per megawatt hour. Few cents per kilowatt hour. 10, 20 years ago, we would not have projected the amount of deployment that we have out there. So we figure out how to do new things in new ways, and we can keep doing that.
Okay, I'll say I'm both determined and also really inspired by the people working in this area, and in particular, not just all of the people here, the scientists and social scientists and policymakers, but really more and more so by the people who are working in kind of the social movement space. And in particular, I'm thinking about the youth climate movement, and I'm thinking about the work we're trying to do on behalf of the youth, and really thinking in kind of that intergenerational way. And I'm incredibly inspired by and grateful to all of those young people who are working in this space, and all of the kind of climate feminists and the voices that are really fighting to be heard, fighting for change, and really being persistent in their insistence that change happen.
I have really just not much else to add, other than I would be honest and say that there are times when I'm panicked, but more just angry and frustrated. But ultimately, I get inspired and hopeful by, as Stephen said, students. If you want a great video clip, look up Michaela King and her recent conversation with John Kerry, just in terms of what her research in Greenland and the massive loss of ice indicates. But she ends on a very hopeful note about just how what we're learning informs just a wiser approach to the future. So I think it resounds with this kind of idea that we as educators are looking constantly to the youth and to the students. And I am hopeful.
Yes, the students are the future. Thank you so much. That was just amazing, and really reflects the way I feel about things as well. So I'm going to hand it back to Joe for a few closing remarks.
Thank you so much, Matt. Wonderful panel. Thank you for getting us all together, and how incredible. It's amazing to be a member of the Ohio State community, the state of Ohio, and to have so many leaders and scientists share a panel with Dr. Katharine Hayhoe. That's just fantastic. And thank you, Matt. I do want to share our certificate of appreciation for those that were on the panel. Robyn and Bryan, I think this is your second one of the year, so your second virtual program. So appreciate it, your continued work with us. And I also want to say this is just our first program of the week with Dr. Hayhoe. So Jeff Sharp, when he introduced the program a couple hours ago, mentioned the collaborators who have been working for over a year to bring, at first in person and now converted to a virtual format, Dr. Hayhoe to our community. And she is speaking at several upcoming events. But while I have the thank you note up here, I do want to mention Karina Peghouse specifically from BIRD. We've heard from so many different staff and faculty associated with BIRD Polar and Climate Research Center, but behind the scenes, Karina was doing an awesome job getting us organized, and then an event that we're having next week, very critical to that. And again, Matt and Brooke and all the folks who helped us write letters and bring Dr. Hayhoe with us. I do want to mention some events that are coming up this week, and these are open to everybody. And I strongly encourage you to spread the word. As I go through each one of these events, Nicole will be posting into the chat box links to learn more or to register. So on Thursday, the Ohio Interfaith Power and Light and the American Scientific Affiliation Ohio chapter are hosting a brown bag lunch with Dr. Hayhoe, where they'll be streaming a previously recorded program talking about building upon shared values to talk about climate change. And then she'll be doing zooming in for a Q&A with Reverend Marcia Dinkins from OIPL to discuss. Following that program, she'll be zooming over to another Ohio-based event, which will be facilitated by COSI. And I really encourage you, if you happen to have children or have family or friends who are learning from home these days, this program is open and will be streamed to the broader public. COSI has a very excellent public outreach platform that they use for this. The CEO of COSI, Frederick Bertley, Dr. Bertley, will be facilitating this dialogue, and that is also on Thursday afternoon. So strongly encourage participation there. And then her final presentation here in Central Ohio will be with the Mid-Ohio Regional Planning Commission on Friday. So maybe there are some who are in the program right now that are planning to participate in that, but it's an excellent opportunity for Dr. Hayhoe for you to spread your message with policymakers, local governments here in the Central Ohio region. I also encourage anyone who is teaching a class right now, or if you're calling in from another university, a college across the state of Ohio, there will be a program that we are facilitating at the EPN with the Byrd Center, as well as with Ohio State's undergraduate student government, focused on conversations about how to develop a career in climate-related work. And we'll have a variety of different breakout groups. Nicole, Karina, and Ohio State's USG help to gather a variety of different environmental professionals who will be talking with students in small groups about ways to turn their passion about climate issues into a potential career. And then lastly, I'll just make a plug for our next EPN virtual event, which will be on November 10th, where we are going to feature the Richland Grow Op, which hosts the Mansfield Micro Farm, as well as a number of other projects that are building community around agriculture. And that'll be with the Center for Cooperatives here at Ohio State, as well as the Sustainability Institute. And we'll have details available to how to register soon. So thank you again so much. That is all for today. Nicole, you're with us. Thank you for everything behind the scenes, and stay safe, be well. And lastly, as Nicole has shared in the chat box, we have been compiling resources that our various panelists, experts have been sharing throughout the session today, as well as some resources that Dr. Hayhoe gave us in advance. So through our automatic message that will go out through the Zoom registration, you will receive a variety of those different resources and links. So stay tuned for that. And we will, as been said before, have all of the programs today edited and recorded up in the near future on YouTube. Thank you all very much. Stay safe and stay well.